All right, welcome. Today, we are putting on our detective hats because we're about to solve a genuine chemical puzzle. We're going to dive deep into empirical and molecular formulas and see exactly how chemists can figure out the true identity of a substance with just a couple pieces of data.
So just imagine this for a second. You're in a lab. You've got this, mysterious white powder. You run a few tests and you find out it's made of carbon, hydrogen, and oxygen. Okay, great. But in what amounts? Is it just simple sugar, or is it something way more complex? That's the core question we're going to crack today. Now, to solve any mystery, you need clues, and we have two main ones. First up, there's the empirical formula. Think of this as the simplest possible ratio of the elements in your compound. Then, you've got the molecular formula, and that's the actual number of atoms in a single molecule. So one's kind of like the basic blueprint, and the other is the finished building.
Let's make it even simpler. Think about baking a cake. The empirical formula is like the basic recipe ratio. For every 2 parts of sugar, you need 3 parts of flour. Simple enough, right? But the molecular formula, that tells you what you actually scooped into the bowl. Maybe you double the recipe, so you used 4 cups of sugar and 6 cups of flour. See? The ratio is exactly the same, but the reality, the actual amount, is totally different.
Okay, let's get this investigation started. First things first, we've got to find that basic ratio, our first big clue, the empirical formula. This is the foundation for, well, everything that comes next. Our detective method here is a pretty straightforward 3-step process. First, we take the percentage of each element and we convert it into moles. This is absolutely crucial because moles let us compare the number of atoms, not just their weight. Then, we find the simplest ratio between them. And finally, we make sure we're working with whole numbers. So let's see how it works in practice. And here it is, the evidence for our case file. Lab analysis tells us our mystery compound is 40% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. Now these percentages are our starting point, but to really compare the atoms, we have to get them into a common unit.
So to make the math super easy on ourselves, we're just going to pretend we have a 100 grams sample. That means we have 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. All we do then is divide each of those by the element's molar mass right off the periodic table. And that gives us the moles of each. And hey, look at that. The mole values for carbon and oxygen are exactly the same. Interesting.
Now for the really cool part, the step that reveals the hidden ratio. We look at our mole values, find the smallest one, which is 3.33, and we divide all 3 of our results by it. And when we do that, bam, we get this beautiful, simple ratio. For every 1 carbon atom, we have 2 hydrogen atoms and 1 oxygen atom. And there we have it, our first major breakthrough in the case. The simplest whole number ratio gives us our empirical formula, CH2O. But hold on. Our detective work is not done yet, not even close. This is just the basic ratio, remember, not the final identity of our compound. All right, it's time for the big reveal. We're going to take this first clue and use it to finally uncover our compound's true identity, its molecular formula. So the real molecule could be CH2O, sure, but it could also be C2H4O2 or C3H6O3 or, some other multiple of that simple ratio. See, the lab techniques that give us the percentages of elements often can't tell us the total size of the molecule. So the big question is, what is that multiple? We need one more piece of evidence to crack this case wide open.
And that final piece of evidence is the molar mass of the actual compound, something we'd get from another instrument in the lab. We use that to find this multiplier, which we just call N. And the formula for it couldn't be simpler. You just divide the molar mass of the real compound by the mass of our empirical formula.
So for our mystery compound, the lab report comes back and tells us the molar mass is 180 grams per mole. We can also really quickly calculate the mass of our empirical formula, CH2O, and that adds up to 30 grams per mole. Perfect. Now we have both pieces of the puzzle. We plug our numbers into that formula, 180 divided by 30, and the number that unlocks this entire mystery is 6. This is our multiplier. This is the key that connects the simple ratio to the complex reality. So, we take our empirical formula CH2O, we multiply every single subscript by 6, and we get C6H12O6. Case solved. Our mystery compound is glucose, the simple sugar that literally powers our bodies. We just went from a few simple percentages all the way to a precise chemical identity. Pretty cool, right? Now, this might all feel like a neat little academic exercise, but I promise you this kind of detective work is happening every single day in labs all across the globe, and sometimes the stakes are incredibly high. Let's talk about why this all really matters.
I mean, think about it. In the world of pharmaceuticals, getting the molecular formula exactly right is the difference between a life-saving drug and something that's totally useless or even dangerous. In the food industry, it's how we get accurate nutrition labels on everything we buy. Environmental scientists are out there using this to identify unknown pollutants, and material scientists use it to engineer the next generation of amazing new materials. It is literally everywhere.
At the end of the day, this whole process isn't just about solving puzzles on a whiteboard. It is a fundamental tool that ensures our safety, it drives innovation, and it helps us understand the world around us at its most basic molecular level. It's everything.
So the next time you look at a nutrition label, or you take some medicine, or even just pour a glass of water, just remember that its chemical formula tells a story that chemists, using these very methods, had to figure out. So, what other secrets do you think are hiding in plain sight, just waiting to be decoded?